Okay, so on homework 10, once again, the first part of this is pretty straightforward, talking about the difference between the photosensors, and that was the lecture from last time about direct reflective, retroreflective. Opaque is something that light doesn't pass through. Translucent, you can see light, and transparent light goes all the way straight through it. Here you can just discern shapes, but the light's blocked a little bit. So that was page 1 of the homework. Most people did pretty well on that. The basic principle of operation was that photoelectrics either sense the presence of light or the absence of light. And most basically you're looking at an emitter that puts out light, and then you're going to collect that light, and then you're going to look for a difference between what you emitted and what you collected, and then it'll sense. We talked about direct versus reflective. Direct goes from the emitter to the collector, basically. It's just a direct beam. If you break the beam, then the signal goes off. Whereas reflective, somehow you've got an emitter and collector here in one unit, and maybe you've got a reflective surface that bounces it back, okay? And then a difference is where you're going to have a combination of these, where these are going to be dual purpose, and see if there's a difference in what was emitted and collected versus here. It could just be completely broken, you know, so you put something in the middle here and it was broke, there's no light. Here we're going to search for the difference. So depending on how accurate you want it to be, okay? And so what I want to do first is look at the questions on 4 to 9, and these were your best guesses about what these were, and I know that these were hard, but we did pretty good with them. So if we take a look at the first one, it says, what scanning technique would be used to sense the top has been placed on a tin can? Well, if I go to page 513, here is 513. It's got all the items here that shows, and the thing that I saw right here was specular. They were showing that objects reflects beam to receiver. So if this is shiny, it would reflect it. And so if you knew your distance, the thing is you have to have, this got to be set up, because you can tell that this was too high, or you know it was too low, then that beam is going to shoot off and go in the wrong direction. But if you know the height of it and it bounces off, it's going to be emit and collected. So I got specular on that first one, I believe. Yep, I went with specular on that one. Moving on to the second one, and some of these people were a little, you know, you were taking a best guess, so I didn't mark you down. I just wanted you to read through the book and see what you got. Well, the next one, scanning for counting number of shiny, opaque containers, or non-shiny, opaque. So they just block light. So if you're going down a conveyor, you got a conveyor side here and a conveyor, and you just pass the beam across here to this side, and it comes down and blocks. That's it. So if I look in my book here again, it looks like we're going to use some type of like a direct scan. You know, this target here, obviously the light can't go through it, so it goes through it, blocks the light, and bang, direct scan. And that's used on conveyors quite a bit. So I can say direct. Which scan would you use for sensing a product wrapped under a shiny, shrink-wrap coating in a brightly lit facility? So what we have here is the brightly lit. So we don't want this to mess up the emitter and collector, or excuse me, the collector, because of the light in the facility. So what we might want to do is you might want to use a polarized sensor. And I'll show you a picture a little bit later about what a polarized sensor is. But basically what that does is it straightens out the light so that if it comes back off. So, you know, maybe some of these other ones could work. This might be one where you would have to try a few different ones and see what works best. Which technique would be used for counting the number of non-shiny, translucent containers passing a point on a conveyor? So now these are non-shiny, they pass a little bit of light, and then they're going on a conveyor. So I've got diffuse on this one, and if I look at my book again on page 513, ease of installation at wiring, on only one side is required, that's good. Exact alignment is not critical. Best scanning technique for transparent or translucent materials, it says for the diffuse. So I'm thinking that a diffuse would probably work in that case. You could also, if they're non-shiny translucent, you might be able to get away with a direct on that one, but maybe one of those two would work. So that one could work. Which scanning technique would be best for verifying the presence of a very small object, such as a pin or a needle? Now, because it's very small, you probably have to use the convergent beam, because like a direct would work, you know, except that a direct field, if you have emitter here and a collector here, you know, this might be shooting light across here, and this width here might be, you know, a quarter of an inch or an eighth of an inch or something like that. So when you put a very small object through there, is it going to catch it? But if you take the light and you converge it through some type of optics or something, then maybe it would fall exactly onto that pin or needle or something like this. And here is an example they show you on page 516, convergent beam. Once again, the thing is, you have to have that distance perfect, because that pin or needle's got to pass through that point. You know, if it passed through here, it might not catch it. So I'm thinking maybe convergent beam on that one. And which scanning technique works best? Where a non-shiny, varying height material, such as corrugated paperboard. Now this is an interesting one. You might have to try a few different ones here, but based on the ones that I got here, I'm thinking maybe diffuse would work, because that cardboard's going to come through, and then what it's going to do is it's going to kind of bounce all over. And if you look in the book here, they've got, you know, this with some bumps on here. So, you know, this light is going to kind of bump to the left, but as this keeps moving through, isn't that light going to kind of get then maybe directed back to here, or directed all over? But eventually, some of that light might come back to here. You know, we use a sensor that's, you know, determining how much of that light's coming back. Maybe as that slides through and that light gets kind of bounced and redirected, some of it's going to get caught there. So maybe, you know, maybe something like that would work. Once again, if that's a tough application, you might have to try a few different ones and see what works. But I don't know if I saw any of those other ones that really looked good there. So those were some of the ones I wanted to look at there. The proximity sensors were all pretty good. Just wanted to remind you, the main ones was an inductive, and that creates an eddy current in metal, because when you have a magnet and you put you know, metal in there, that's going to kind of affect the magnetic field, right, due to the nature of the metal, and then you'll create an eddy current, and then that's kind of how that inductive proc's working on metal. The capacitive was a capacitive field, and same thing. It had a dielectric constant, and it senses just about anything that capacitive does, because that dielectric constant is usually large enough. And so that was the principle there, and we demonstrated that in lab. And the basic principal operation of the Hall effect is the magnetics. And once again, you've got a magnetic field, and when you put you know, some type of metal or something, interact it with a magnetic, well, that's going to set up the current in the sensor, and that you can sense that. Okay, so that was pretty good there. And then distance and operating items of the capacitive products are basically in the Hall effect. It's the type of material, the size of the material, the distance that the material is from the detector, the sensitivity of the detector, things like that. So those are some things that when you sense out a proximity sensor that you would want to keep in mind.